Okay. So finally, they have zero mean and the same variance, so we can use our correlation measure. So what's the expected value of u times v? That is equal to the expected value of 0.8x plus 0.6y plus 0.6x plus 0.8y. So this is equal to 0.8 times 0.6 x squared which is 0.48 x squared plus 0.8x times 0.8y 0.64 xy plus 0.6y plus 0.6x, which is 0.36 xy, plus 0.6y, 0.8y, which is 0.48 y squared. Okay, distributing the expectation, expected value of x squared is what?
1.
It's 1. X squared, that's the variance of x, that's 1. Expected value of x times y?
0.
0. 0. Expected value of y squared? 1. So we have 0.48 plus 0.48, which is what? 0.96. So what does this tell us? For one thing, it obeys the rules that I discussed. The variance is equal to 1, and this is less than the variance. For another thing, it's not the max, so it's not only not equal to the variance, it's less than the variance. So these are not completely correlated, but because it's so close to the variance, we can argue that these two random variables are actually very highly correlated. And that kind of makes sense because we have each random variable contains a very large component of the other. So this has 0.8 of x and this has 0.6 of x. This has 0.6 of y, that is 0.8 of y. So we would expect that these two random variables are very highly correlated, and that's exactly what this is telling us. Yes?
Is correlation with the normalized value usually between -1 and 1?
Yes, you can normalize it. All you would do then is divide by the variance.
Saying it's more correlated than 100% doesn't make sense.
I see what you're saying. So in this case, we're comparing it to the variance. So if my variance was 20, this would end up being 0.96 times 20. So you can in some applications you normalize it. What you do there is you just divide out the variance. So yeah, you can totally do that. Okay, so let's switch back to autocorrelation. So what is autocorrelation? It's exactly the same thing, except taking two values of random process. So expected value, x of t1, x of t2. So again, let's see a couple examples of this. By the way, let's give this the notation r sub x of t1, t2. So remember, my symbol for correlation was r. So that's incorporated here. I'm still r for autocorrelation. That's the x is the random process, and t1 and t2 are the two time instants. So let's have a couple of random processes. Firstly, a Gaussian random process. X, where the variance of x and t. So remember, we discussed last time that the mean and variance can be functions of time, but here I'm going to say they're constant with respect to time. The variance is equal to 1 for all t. The mean, expected value of x of t, is equal to 0 for all t. And furthermore, I'm going to say x of t1 and x of t2 are independent for all t. So this is an independent Gaussian random process where each time I examine the process, it's independent. Independent for all t if t1 not equal to t2. For all t1, t2 if t1 is not equal to t2. Okay. What is the autocorrelation? Rx of t1 and t2 expected value xt1, xt2. Okay, we have to express this as a function of both t1 and t2. So, what is the value of expected value of t1, t2? Any ideas how to start? So we know that they're independent if t1 is not equal to t2. So we also know that the mean is 0. So what does that suggest about this?
Also 0?
It's 0, but when?
When t1 is equal to t2.
That's right. So we have Rx. So if t1 is not equal to t2, then this is equal to the expected value xt1, expected value xt2, which is 0 times 0, which is 0. Okay, if t1 is equal to t2, what do I have?
Then it's 1.
Then it's 1. So if I have this then equal to expected value x of t1, I can substitute, because t1 and t2 are equal, I can substitute t1 for t2. So I have the expected value of x of t1 squared, which is equal to the variance of x of t because the mean is 0. That's equal to 1. So if I express this as a function of t1 and t2, I can say Rx, t1 and t2 is equal to 1 if t1 is equal to t2, and 0 if t1 is not equal to t2. So if I were to plot that on a 2D grid, that would mean in all these diagonal elements,